Imagine you could reach into the sky, lift our sun out of the centre of the solar system, and set a different star in its place. Not a bigger sun, a monster. A star so enormous that the moment it settles in, Mercury is gone, then Venus, then the Earth, then Mars, and even Jupiter, all of them swallowed inside a single ball of red light with room left over. This is not a fantasy. 15,000 light-years away, hidden behind a curtain of dust in the most crowded stellar city in our galaxy, that exact star is real, and we have measured it. It is one of the largest things human beings have ever found, and almost no one knows its name. So what would it take to build a star that size, and why is something so enormous already running out of time? Get comfortable and settle in. Subscribe if you have not already, and stay with us, because to really feel the size of this star, we're going to travel all the way to it and watch what happens to everything we thought was big along the way. Let's get into it. Part 1. The Invitation to Leave. Right now, above your head, past the blue of the sky and the darkness that begins just beyond it, there is a star so large that our entire inner solar system could vanish inside it, and the star would not even register the loss. Not the Earth, not Mars, not Jupiter. All of it, swallowed, with room left over. And here is the strange part. You have almost certainly never heard its name. It does not shine in our night sky. You could stand outside on the clearest, darkest evening of your life, look straight toward it, and see nothing at all, because between us and this monster lies 15,000 light-years of space, and an ocean of dust so thick that it hides the star behind a curtain 100,000 times too dark to see through. For most of human history, we had no idea it was there. We know now, and the way we found it is where this story begins. In the year 2017, astronomers turned the Hubble Space Telescope toward a small, unremarkable patch of the southern sky, in a direction most people will never look, low in a faint constellation called Ara, the Altar. There is not much to see there with the naked eye. It sits close to the crowded band of the Milky Way, in a region so clogged with interstellar dust that early astronomers called it part of the zone of avoidance, because the dust seemed to push the stars away, hiding whatever lay behind it. But Hubble does not look the way your eye looks. It can gather light for a long time, and it can pick out the faint infrared glow that slips through the dust when ordinary light cannot. And when the image finally resolved, it showed something remarkable. Hidden behind that veil was a city of stars, not a handful, not a few dozen, a tightly packed swarm of hundreds of thousands of suns, crowded into a space so small that if you lived on a world inside it, your night sky would blaze with the light of stars brighter than any we have ever seen from Earth. This place has a name too. It is called Westerlund 1, after the astronomer who first noticed it back in 1961, and it is the most massive young cluster of stars we have ever found in our galaxy. But the cluster is not why we're making this journey. We're going there for a single one of its residents. Somewhere in that crowd sits a star catalogued with the plain, forgettable label Westerlund 1-26. And that star, that one quiet entry in a list, is one of the largest single objects ever measured by human beings. I want to take you there. Not with a diagram and not with a chart, but by travelling, the way you would if you could climb into a ship and point it across the galaxy. We are going to leave the sun behind, cross 15,000 light-years of open space, pass through the outskirts of that hidden city, and stand in front of the monster itself. Along the way, the scale is going to keep changing under your feet. Things that feel enormous right now, the sun, the solar system, the distance to the nearest star, are going to shrink one by one until they feel almost quaint. That is the whole point of the trip. By the time we arrive, you're going to understand the size of this star not as a number, but as a feeling. So get comfortable, and let me show you what is out there. Picture where we start. You're floating just above the plane of the solar system, looking back at the sun. From here it is still overwhelming, a blinding disk pouring out heat and light, the anchor that holds every planet in its slow orbit. It is the largest object for light years in any direction, a ball of glowing gas so wide that you could line up more than 100 Earths across its face and still have space to spare. Everything you have ever known has happened inside its reach. Now we begin to move. The sun slides away behind us, and watch what happens to it. First, it stops being a disk and becomes simply a very bright star. Then, as the light years fall away, it dims and shrinks until it is one point of light among many, no brighter than its neighbours, impossible to pick out unless you already knew exactly where to look. The thing that rules our entire sky becomes, from only a little way out, an anonymous speck. Hold on to that feeling. We are going to meet it again at the end of this journey, and it is going to mean something different then. As we pick up speed, the stars begin to stream past us, and I want you to really look at them, because it is easy to let them turn into scenery. Every single one of those points of light is a sun, not like a sun, a furnace of the same kind that warms your face on a summer afternoon, burning through its fuel across millions or billions of years, many of them circled by planets of their own, some of those planets warm, some of them wet, some of them perhaps, looking back toward us and wondering the same things we wonder. When you stand in a field at night and see a few thousand stars, you are seeing a tiny local sample of 400 billion suns that make up our galaxy alone. Every dot is a sun. I am going to say that again before this is over, because by the end it is going to carry more weight than it does right now. For a long stretch there is nothing to do but travel, and that is its own kind of wonder. The distances out here are so enormous that light itself, the fastest thing in existence, crawls across them. The light now entering your eyes from these passing stars left them centuries ago, some of it before you were born, some of it before anyone alive was born. We are moving through a stretch of space where the present tense barely applies. Where to look outward is to look into the past, and somewhere ahead of us, still too far to distinguish from its neighbours, our destination is waiting, its light already on its way toward us, having left the star 15,000 years ago, when the last ice age still gripped the Earth and no city yet existed anywhere on the planet. Then, low on the left side of your view, you begin to notice it. A single reddish point, no more impressive than a dozen others nearby, but it does not slide past the way the others do. It holds its place, dead ahead, and slowly, patiently, it grows. That red point is where we're going. It does not look like a monster yet. It looks like a warm ember floating in the dark, almost gentle. That is the trick this star plays on everyone who approaches it. From far enough away, the largest things look small and harmless, the same way the sun looked small and harmless once we had put a little distance behind us. Before that red point grows any larger, let me give you a sense of the direction we're travelling, because it matters that this star sits where it does. Look toward the southern sky, toward a small, faint constellation the old astronomers named Ara, the Altar. It is not a part of the sky most people could find. There are no famous bright stars there, no shape that leaps out, nothing to draw the eye. If you grew up in the northern half of the world, you may never have seen that patch of sky at all, since it sits low toward the southern horizon, and yet that unremarkable, easily missed direction is where one of the largest stars in the galaxy has been hiding the whole time, tucked behind the dust, waiting. There is something humbling in that. The most enormous things are not always where we are looking. Sometimes they sit in the plainest, quietest corner of the sky, and it takes us thousands of years and the right instrument to even notice they are there. Feel the speed we would need to make this trip in any reasonable time, because it tells you something about the gulf we are crossing. Even if we could somehow travel at the speed of light itself, the fastest anything is allowed to go, this journey would still take 15,000 years. We would leave today and arrive 15,000 years from now, and everyone we had ever known would be long gone, their entire era turned to history and then to legend and then to nothing anyone remembered. That is not a distance you cross. It is a distance you fall through generation after generation. In our simulation we are cheating, folding all of that time into a smooth, swift glide. But I do not want you to lose the truth of it. Real space is not the tidy map in a textbook. It is an ocean so wide that light itself grows old crossing it, and we are skimming over the top of it toward a single red point that has been sending us its light since before the first farmer planted the first seed. We're still a long way out, and before we can reach that ember we have to pass through the strange, crowded neighbourhood it calls home, a place unlike anywhere near our own quiet sun. Because a star like this one does not form alone, in a peaceful corner of space. It is born in a crowd, in a place violent enough to make it, and that crowd has a few things to show us first. Part 2. A Galaxy of Suns. The crossing is going to take a while, And I think that is worth sitting with, because the emptiness between the stars is a part of this story that almost never gets told. We talk about the galaxy as a crowded, glittering place, and from a distance it looks like one. But the space between one star and the next is almost unimaginably empty. If you shrank the sun down to the size of a single grain of sand and set it on a table, the nearest other grain of sand, the nearest neighbouring star, would be roughly 6 miles away. Between those two grains there would be nothing but a few stray molecules drifting in the dark. That is the normal condition of our galaxy. Stars are lonely. They keep their distance. Our sun has drifted through space for 4.5 billion years without ever coming close to another star, and it never will. Hold that picture in your mind, because it is going to make our destination so much stranger when we arrive. Where we're going, the stars are not grains of sand 6 miles apart. They are packed so tightly that thousands of them crowd into the space where our sun sits alone. But we're not there yet. For now, we're still in the quiet, moving through the ordinary galaxy, and the stars continue to slide past us one at a time, each one a sun. I keep coming back to that phrase, and I want to explain why. When you look up at night, your brain files the stars away as decoration, little lights on the ceiling of the world. It is almost impossible to feel what they really are. But every one of them is a churning ball of fire, larger than anything you will ever stand next to, converting millions of tons of matter into light every second, and has been doing so since long before humans existed. Some of the ones we're passing are older than the Earth, some of them are younger than the dinosaurs, some of them have planets, and on a few of those planets there may be oceans and weather and slow chemistry that has been working away for ages toward who knows what. We will never visit almost any of them. They are simply too far apart, and yet here they are, uncountable, streaming past us, each one a world unto itself. Every dot is a sun. Consider how far we are actually travelling. The distance to this star is around 15,000 light years. A light year is the distance light covers in a year, and light is not slow. It could circle the entire Earth about 7.5 times in a single second. In 1 year it crosses nearly 6 trillion miles. Now multiply that by 15,000. The number stops meaning anything, which is exactly the problem with space. The human mind simply does not have a shelf to put a number like that on. So let me try it a different way. The light that is arriving at the star right now, the light we are chasing, left the sun 15,000 years ago. When it departed, there were no farms anywhere on Earth. No writing, no wheels. Human beings were still living as hunters at the edge of retreating glaciers. Every single thing we call history, every city and empire and invention, has happened in the time it takes light to make this one trip. We are crossing a gulf so wide that civilizations rise and fall in the gap. There is something else the distance hides, and it is a little unsettling. Because the light takes so long to reach us, we never see this star as it is. We see it as it was, 15,000 years ago. Everything we are about to learn about it, everything astronomers have measured, describes a version of the star that existed before the pyramids, before the first written word, before recorded time. What the star is doing right now at this exact moment is a message that has not arrived yet and will not arrive for 15,000 more years. Out here, the word now loses its footing. To look into space is to look into the past, and the farther you look, the further back in time you go. We are not just crossing distance, we are crossing time. As we travel, that single red point we noticed earlier has not stayed a point. It has been slowly resolving, the way a distant town at night resolves from a smudge of glow into individual windows as you approach. What looked like one reddish ember is beginning to separate into many lights, and around it, a faint haze is sharpening into a dense knot of stars. The colour is unusual. Most of the region carries the hot white and blue of young, powerful stars, the kind that burn fierce and fast. But among them, a few points glow with a sullen ember red, and one of those red points is brighter and steadier than all the rest. That is our monster, still small in the distance, still wearing its harmless mask. We are approaching the edge of its home. Slow down with me here, because the first sight of this place deserves a moment. Ahead of us is a swarm of stars unlike anything in our corner of the galaxy. Where the sun drifts alone, here there are hundreds of thousands of stars crammed into a knot only a few light years across, so close together that they light each other up. If you took all the stars you can see on the darkest night from Earth, every last one, and swept them into a space smaller than the distance between the Sun and its nearest neighbour, you would begin to approach the crowding here. And these are not gentle stars. Many of them are giants, blazing with the raw power of youth, the kind of stars that live hard and die young and violent. This whole place is only a few million years old, which sounds ancient, but for a cluster of stars is practically newborn. We are looking at a stellar nursery that has already started producing monsters. Think about what it would mean to live inside a place like this. If the Earth orbited a star somewhere in this crowd, our night sky would not be a scattering of faint pinpricks. It would blaze. There would be stars bright enough to cast shadows, stars brighter than the full moon, a sky so crowded with brilliant light that true darkness might never come at all. It would be beautiful beyond anything we know, and it would also be dangerous because a place that makes stars this large also destroys them, regularly and spectacularly, in explosions powerful enough to sterilize the worlds nearby. Beauty and violence, tangled together. That is the neighborhood our monster was born into. That is the kind of place it takes to build something this size. Consider how strange it is that the galaxy manages to look crowded at all, given how empty it truly is. When you see a photograph of a galaxy, a bright swirl packed edge to edge with light, it looks like the stars must be jammed together, practically touching. They are not. That solid-looking glow is an illusion of distance, the way a distant forest looks like a solid wall of green when really it is mostly air and open space between the trees. If you stood inside the galaxy and looked around, which of course you're doing right now, you would see darkness sprinkled with points of light, and between any two of those points, an emptiness so wide it takes years for light to cross. The galaxy is not a crowd. It is a scattering of lonely fires in an enormous dark room, each one so far from the next that they can barely be said to be neighbours at all. This is exactly why the place we are heading is going to feel so wrong when we arrive. Everything about normal space says stars keep their distance, that they are solitary by nature, that the room between them is the rule, and the stars are the rare exception. And then, ahead of us, is a knot of space where that rule has been broken so completely that hundreds of thousands of stars are packed into a pocket a few light years wide, close enough to light one another up, close enough that on a world among them there would be no true darkness at all. To go from the lonely emptiness of ordinary space into a crowd like that is to cross from one kind of universe into another, and the fact that a place that crowded is exactly the kind of place needed to build a star as large as the one we came to see is not a coincidence. It is the whole reason we had to come all this way to find one. We are almost at the threshold now, about to cross from the empty galaxy into the crowded city where this star lives, and I want to prepare you for something, because when we finally pull up alongside our destination, your first reaction is going to be disappointment. After all this build-up, after 15,000 light years and a warning about monsters, the star is going to look, for just a moment, almost ordinary. That first impression is a lie, and it is a lie the numbers are about to expose in a way you will not forget. Because this quiet red star is hiding a size that our minds were simply never built to hold. Part 3. The most crowded city in the galaxy. We have crossed the threshold, and the cluster is all around us now, so let me tell you exactly where we are, because this place has a reputation among astronomers. It is called Westerlund 1, and it holds a record. Of all the young star clusters we have found anywhere in the Milky Way, this is the most massive. Packed into a region only a few light years across is something like 100,000 times the mass of the Sun gathered into stars. To put that in perspective, that is 100,000 suns worth of material crushed into a space so small that, on the scale of the galaxy, it is a single bright point. Our own Sun sits in a comfortable, roomy suburb where the nearest neighbour is light years away. Here, the neighbours are practically on top of each other, thousands of them where we would expect one. The whole cluster is young, which is part of why it is so interesting. Astronomers estimate its age at somewhere between 4 and 5 million years. That may sound impossibly old, but stars measure time differently than we do, and by their reckoning this cluster is a newborn. Our Sun, for comparison, is about 4.5 billion years old, roughly 1,000 times older than everything around us here. All of these stars form together in a single enormous burst of starbirth, out of one giant cloud of gas and dust that collapsed and fragmented into hundreds of thousands of pieces at nearly the same moment. They are siblings, in a sense, born from the same cloud, and they are still clustered close to their birthplace because they have not had time to drift apart. Look at what that single burst produced. Scattered through this crowd are some of the rarest and most powerful kinds of stars in existence. There are around 24 Wolf-Rayet stars here, which are among the hottest and most furious stars known, aging giants that have blown away their outer layers and now blaze with naked, savage light while their surfaces boil off into space. There are 6 yellow hypergiants, enormous unstable stars that are relatively rare across the entire galaxy, and yet here are half a dozen of them in one small cluster. There is a luminous blue variable, one of the most temperamental kinds of star we know, capable of erupting without warning. There are many hot, massive supergiants of the type that live fast and explode. And there are 4 red supergiants, the cool, swollen giants near the ends of their lives. One of those 4 red supergiants is our destination. Think about what that census is telling us. Nearly every kind of extreme, short-lived, spectacular star that the universe can make, this one cluster has made, all at once, all in the same neighborhood. It is not a quiet residential street. It is a factory for the most violent objects in the galaxy. And that is not a coincidence. It takes an enormous, crowded, dense collapse of gas to build stars this large, and only a place like this, forming 100,000 suns in a single event, has the raw material to do it. The monster we came to see could not have been born beside a quiet star like our own. It required this. It required a crowd. There is a price for all this brilliance, and it is worth naming, because it is part of what makes this place feel so different from home. Stars this large do not last. The most massive of them will burn through their entire fuel supply in just a few million years, and then die as supernovae, detonating with a force that briefly outshines whole galaxies. In a cluster this size, with this many giant stars, that is not a rare event. Astronomers estimate that Westerlund 1 produces a supernova roughly once every 10,000 years. On a human timescale that sounds gentle, but consider what it means. Every 10,000 years or so, somewhere in this crowd, one of these giants tears itself apart in an explosion violent enough to strip the atmosphere off any planet unlucky enough to be nearby. This is a place of continuous rolling destruction, a neighborhood where the residents keep detonating. Beauty and violence again wound together so tightly you cannot separate them. I want you to imagine standing on a world somewhere inside this cluster, just for a moment, because it will tell you something no number can. The sky above you would be unrecognizable. Instead of the few thousand faint stars we see from Earth, you would be surrounded by a wall of brilliant suns, some of them close enough to show as tiny disks rather than points, many of them bright enough to cast shadows on the ground, several of them glowing in colours, hot blue and searing white, and, here and there, that ominous ember red. There would be no true night. The darkness we take for granted, the black sky that let our ancestors first wonder what the lights were, would simply not exist here. And every so often, across the generations, one of those brilliant points would flare into something unbearably bright, brighter than everything else in the sky combined, and hold there for weeks before slowly fading, another giant gone. It would be the most beautiful and the most frightening sky imaginable. It is the sky our monster was born under. It is worth pausing on how we know any of this, because the honest answer is that for a long time we did not. This entire cluster sits behind those thick curtains of dust I mentioned, dimming its visible light by a factor of around 100,000. For most of the history of astronomy it was essentially invisible, just another dark patch near the crowded band of the Milky Way. It was not until 1961 that the astronomer Bengt Westerlund, working under the southern sky, first picked out the faint infrared glow leaking through the dust and realized there was something hidden back there. Even then, it took decades more, and instruments far more powerful than anything he had, to understand what he had found. When the Hubble Space Telescope finally turned its attention here and gathered the light long enough, the hidden city snapped into focus, and astronomers could begin to take a real census of its residents. That is the discovery in the title of this journey. That is what Hubble revealed. Not a new dot in the sky, but the true nature of a monster that had been hiding in plain sight, waiting behind the dust for someone to build an eye sharp enough to see it. And now that our eyes are sharp enough, let me point you toward the one we came for. Among all these blazing blue and white giants, your attention keeps getting pulled back to a single reddish star near the center of the crowd. It does not have the searing brilliance of the Wolf-Rayet stars around it. Its light is cooler, calmer, the color of a dying coal. In a photograph you might pass right over it, one red dot among thousands of brighter points. That unremarkable red dot is Westerlund 1-26. That is the whole reason for this trip. And as we turn toward it and begin our final approach, I need to warn you one more time about the trick it plays, because it is about to play it on you. To feel how unusual this cluster is, it helps to know how rare these kinds of stars are everywhere else. Take the Wolf-Rayet stars, those furious aging giants boiling their outer layers away into space. Across the entire Milky Way, a galaxy of 400 billion stars, we know of only a few hundred of them, because a star spends only a geologic eye blink in that phase before it dies. They are needles in an enormous haystack, and yet here, in this one small cluster, there are around 24 of them at once, gathered in a pocket you could cross in a few years at the speed of light. The same is true of the yellow hypergiants, which are among the rarest stars known anywhere, with only a handful confirmed in the whole galaxy, and 6 of them are right here. Statistically, this should not happen. You do not find that many of the rarest, most short-lived stars in the universe sitting together in one place by chance. The only way it happens is if they were all born together, at the same moment, from the same collapsing cloud, and if that birth event was enormous enough to make hundreds of thousands of stars in one go. That is exactly what Westerlund 1 is, the fossil of a single colossal act of star formation a few million years ago, caught in the brief window before its biggest members start dying off. We are not looking at a random sample of the galaxy. We are looking at a graduating class of giants, all the same age, all racing toward their ends together, and the largest of them all is the one we came to meet. We are close enough now to see the star as more than a point, and here comes the disappointment I promised. It looks at first like a perfectly reasonable star, a warm red glow, steady and calm, sitting quietly among its flashier neighbours. Your instinct is going to say, that is it? That is the monster? And I understand the reaction, because from this distance nothing about it screams danger or record-breaking size. But that instinct is about to fail you completely, the same way your instinct about the sun failed you when we watched it shrink to a speck. Size at these distances is almost impossible to judge by eye. The only way to feel what this star truly is to stop looking at it and start measuring it against things you already understand. So that is what we're going to do next. We're going to take this quiet red star, and we're going to bring it home, and we're going to set it down exactly where our sun now sits. And what happens to our solar system when we do is going to be very hard to forget. Part 4. The star that doesn't look like much. Let me start with the one number that matters most, and then spend the rest of our time together making it mean something. Westerlund 1-26 has a radius that astronomers most often place at somewhere between 1100 and 1200 times the radius of the Sun. When they estimate it a different way, using how much light it pours out, the figure climbs toward 1500 times the Sun's radius. There is even an extreme upper estimate, which most researchers think is unlikely, that pushes past 2500. I am going to be honest with you throughout this journey about which numbers are solid and which are shaky, because the uncertainty is part of what makes this star fascinating. But hold on to the middle of that range. This star is somewhere around 1000 to 1500 times wider than our Sun. Now let me try to turn that into something you can actually feel, because on its own it is just a big number, and big numbers slide right off the mind. Start with the Sun, because even the Sun is already too large to picture honestly. Our Sun is about 860,000 miles across. You could line up more than 100 Earths side by side along its width, and still not reach the other edge. If the Sun were a hollow ball, you could pour more than 1 million Earths inside it. Everything about the Sun already breaks the human scale. It is the largest thing any of us will ever be in the presence of, and now I am telling you to take that Sun, that impossible million-Earth furnace, and imagine it as the small object in the comparison. Because our monster is not 100 times bigger than the Earth. It is more than 1,000 times bigger than the Sun. Try to build it up in stages, because that is the only way a number like this has any chance of landing. Imagine the Sun floating in front of you at some manageable size, say the size of a beach ball. On that scale, the Earth would be a grain of salt sitting about 100 feet away. That is already a lopsided comparison, the beach ball and the grain of salt. Now, to represent Westerlund 1-26 on that same scale, you would have to throw the beach ball away and replace it with a sphere more than 1,000 times wider, something well over 1/4 of a mile across, a glowing ball large enough to swallow a small town, with that same grain of salt Earth lost somewhere far inside it. That is the jump we're talking about. Not from the Earth to the Sun, but from the Sun to this. Here is another way in, through sheer volume, through how much space the thing occupies. When you make an object 1,000 times wider, its volume does not grow 1,000 times. It grows 1,000 times 1,000 times 1,000, because volume climbs in all three directions at once. Run that out, and you find that Westerlund 1-26 holds roughly 1 billion times the volume of the Sun. 1 billion! If the Sun were hollow, you could pour 1 billion suns into this star, and they would rattle around inside it. And since a single sun could already swallow more than 1 million Earths, that means the number of Earths you could fit inside this one star runs into the quadrillions, a number with so many zeros that writing it out does nothing for you at all. This is where language starts to fail, and I think it is important to admit that rather than paper over it. There is no honest way to make you feel a quadrillion. The mind simply does not go there. What we can do is keep circling the size from different directions, hoping that one of them slips past your defences and lands. So let me stop with the multiplication for a moment and just tell you what you are looking at as we pull up alongside it. The star fills your view now, and it has stopped looking like a point or a disk. It has become a wall, a curved, glowing surface of dull red light that stretches away in every direction until it curves out of sight, with no visible edge, no clean line where the star stops and space begins. It does not glare like the sun. Its light is cooler, the colour of a fading coal or a warm sunset, because its surface is only about 3,000 degrees, roughly half the temperature of the sun's surface. It is enormous and it is calm, and there is something almost peaceful about it, right up until your mind does the arithmetic of what you're actually seeing, and then the peace curdles into something closer to vertigo. This is the moment I've been leading you toward, so let me slow all the way down and let it arrive properly. You're floating in front of a single star, not a galaxy, not a nebula, not a cluster of 1,000 objects. One star, one sun, of the same basic kind that anchors our solar system. And this one object, this single burning sphere, is so large that if you could somehow stand at its base and start walking, and if you could walk on the surface of a star, and if you never stopped, it would take you longer to walk around this one star than it has taken light, travelling at the fastest speed the universe allows, to reach here from the far side of it. Everything you have ever known, every person who has ever lived, every event in all of human history has happened on a grain of salt orbiting a beach ball. And here, 15,000 light-years away, hidden behind a curtain of dust in a crowded stellar city, sits a single object that could hold that beach ball and that grain of salt and the entire space between them, over and over, with room left over. It is not a painting. It is not a thought experiment. It is a real thing, measured by real instruments, that exists right now, casting its red light out into the dark whether or not anyone is there to see it. I think the reason a fact like this is so hard to hold is that our minds are built for the scale of our bodies. We evolved to judge the size of a predator, the distance across a river, the height of a tree. We have good instincts for those. We have no instincts at all for this, and when we come face to face with it, the mind does a strange thing. It flinches. It reaches for the number, fails to feel it, and quietly files the star away as just another big thing, no different from a mountain or an ocean or the sun itself. I want to ask you to resist that flinch, just for tonight. Do not let this become just another big number. Sit in the discomfort of it for a moment. There is a real object out there so large that our language and our imagination both give out before we reach the edge of it, and the fact that we can measure something we cannot picture is one of the strangest and most wonderful things about being human. Let me offer you one more way to hold this size, because I have found it is the comparison that finally makes people go quiet. Forget the sun for a moment and think about a passenger jet, the kind that crosses an ocean in a handful of hours, moving at around 600 miles an hour. If you could somehow fly that jet all the way around the Earth, without stopping, it would take you about 2 days. 2 days to circle the entire planet, every ocean and continent at the speed of a jet airliner. Now take that same jet and fly it around the sun. At 600 miles an hour, that trip would take you not 2 days, but around 6 months. And now fly it around Westerlund 1-26. That same jet, moving at the same speed, never stopping to rest or refuel, would need something like 1,000 years to make a single loop around this one star. 1,000 years. Empires would rise and fall in the time it took you to fly once around a single sun. Sit in that for a moment, because it is real. A journey that would take 2 days around our whole planet would take 10 centuries around this star, at the same speed. Generations of pilots would be born, fly their leg of the trip, hand the controls to the next generation, and grow old, all without completing one lap. That is not a number on a chart. That is a distance measured in human lifetimes laid end to end. And this is a single star, one object, one of the same kind of things that hangs quietly in our sky every night. When I say this star breaks the human scale, this is what I mean. It is not just larger than we can picture, it is larger than our whole framework for picturing things, and the only honest response is a kind of stunned silence. Now, I have been describing this star's size by comparing it to the Sun, which is fair, but comparisons to the Sun are still abstract, because none of us has ever really held the size of the Sun in our hands either. So we are going to do something more concrete, and frankly, more alarming. We are going to take Vestalun 1-26 out of its crowded city, carry it 15,000 light-years back home, and set it down in the one place where its size will finally truly land. We are going to put it exactly where our Sun sits right now, at the centre of our solar system, and we are going to watch what happens to the familiar map of planets we all grew up with. Because that is where the abstract turns personal. That is where this stops being a story about a distant star, and becomes a story about the ground under your feet, the sky over your head, and just how much of everything you have ever known would simply cease to exist inside the body of a single, quiet, red star. Part 5. If it replaced our Sun. Let us perform the swap. In your mind, lift our Sun out of the centre of the solar system, that familiar yellow furnace that every planet circles, and set it aside. In its place, lower down Westerlund 1-26, our red monster, centred exactly where the Sun used to be. Everything else stays where it is for now. The planets keep their orbits, the same paths they have traced for 4.5 billion years. And now let us look at what happens, planet by planet, as this new Sun settles into place. Mercury goes first, and it never had a chance. Mercury orbits the Sun at about 40% of the distance between the Sun and the Earth, hugging in close. The new star's surface reaches out far past that point, so Mercury is not scorched or melted. It is simply inside the star, gone, its entire orbit swallowed into the glowing body of the giant. Venus is next, orbiting at about 70% of the Earth's distance, also inside, also gone. Then comes the Earth, our own world, at the distance we define as 1 astronomical unit, the standard yardstick of the solar system. The Earth's entire orbit, the full circle our planet travels in a year, fits comfortably inside this star with the room to spare. If you were standing on the Earth at the moment of the swap, there would be no sunrise to watch, there would be no sky. You would already be far inside the body of the star, along with the whole path of our orbit, a tiny grain lost inside something 1,000 times wider than the Sun that used to warm you. Keep going, because it does not stop at Earth. Mars orbits at about 1.5 times the Earth's distance, out where the sunlight is already weak and the world is cold. Mars is inside the star too, and now we reach the giant of our own solar system, Jupiter, orbiting more than 5 times farther from the Sun than the Earth does, so far out that sunlight takes the better part of an hour to reach it. Surely Jupiter, the king of our planets, is safe. It is not. By the middle range of the estimates, the surface of Vestalun 1-26 reaches out past Jupiter's orbit as well. The largest planet in our solar system, a world that could swallow 1,300 Earths, would itself be swallowed, its entire enormous orbit tucked inside the body of this single star: Mercury, Venus, Earth, Mars, and Jupiter. The inner solar system and its giant, all of it, inside one star, and still there is room to spare. I want you to hold on to that phrase, room to spare, because we're going to come back to it more than once before this journey ends, and each time it is going to mean something a little different. Right now it means abundance, excess, a size so enormous that after devouring everything out to Jupiter, the star has not even reached its limit. By the highest estimates, the ones most astronomers treat with caution, the surface would stretch out toward the orbit of Saturn itself, nearly 10 times the Earth's distance from the Sun. Even at the more conservative numbers, everything you think of as the solar system, everything except the outer giants and the cold dark beyond them, would be gone. One star. Room to spare. Let me give you a different handle on this size, one that I find lands even harder than the planets, because it uses the fastest thing in existence as a measuring stick. Light travels at about 186,000 miles every second, so fast that for anything on a human scale it may as well be instant. Light could travel around the entire Earth in about 1/10 of a second. If you wanted to send a beam of light around the whole planet Jupiter, the largest planet we have, it would take about 1.5 seconds. To send light all the way around our own Sun, that impossible million-Earth furnace, would take about 14 seconds. 14 seconds for light to lap the Sun. Now, how long do you think it takes light to travel just once around Westerlund 1-26? Not 14 seconds, not 14 minutes, about 6 hours. Light. The fastest thing there is, the thing that crosses from the Sun to the Earth in 8 minutes, would need most of a working day just to make a single loop around this one star. That is the size we are standing in front of. Let me put you somewhere to watch this, because I think you need to see it, not just calculate it. Come with me out to Saturn and stand on the surface of one of its icy moons, looking back toward where the Sun should be. In our real solar system, from all the way out here, the Sun is reduced to a brilliant point, small enough to hide behind a pinhead held at arm's length, though still bright enough to cast a pale light across the ice. That is our Sun from Saturn. Now make the swap again. Replace that distant point with our monster. Where there was a bright pinhead, there is now a wall of dull red light that fills a huge section of the sky, so large that you cannot take it in with a single glance. It does not rise or set cleanly. It simply looms, a curved red horizon of fire hanging over the ice, its surface slowly churning, close enough that you feel you could reach out and touch it, even though it is still hundreds of millions of miles away. There is no comfortable way to look at it and no way to look away. The whole moon beneath your feet glows red in its light, and you realize, standing there, that you are parked at the distance of Saturn, out at the cold edge of everything, and this star still dominates your entire sky. That is what it would mean to trade our modest Sun for this. The red light falling on that ice hints at something else about this star, something we have not talked about yet, and it is the other half of what makes it a monster. It is not just enormous, it is outrageously luminous. Because its surface is cool, only around 3,000 degrees, its light is that calm ember red rather than the fierce white of a hotter star. But it is so unimaginably large that even at that cool temperature, the total amount of light it pours out is staggering, somewhere between 300,000 and nearly 400,000 times the output of the Sun. Every second, this star radiates as much light as several 100,000 suns, and that fire hose of light does not stay local. It reaches out across the galaxy. In fact, the light is so intense that even from thousands of light years away, if the dust were cleared, this single star would stand out as a distinct red point. In a simulation where you pull back from the star and keep going, until you have left the entire cluster behind, until you're drifting out past the edge of the galaxy itself and looking back at the whole pinwheel of 400 billion suns, you can still find Westerlund 1-26, a faint red spark, refusing to disappear, a beacon that will not go out. Remember that image, that stubborn red spark still visible after you have left the galaxy behind. We're going to return to it at the very end, under circumstances you will not expect. Stay on that icy moon a moment longer, because there is a consequence to standing under a star like this that the simulation does not show you, and it is worth facing. A sun that fills a huge section of your sky is not just a spectacle, it is a furnace, and everything beneath it cooks. If our real sun were swapped for this monster, the inner solar system would not simply be swallowed. Everything else, every world that lay outside the star's body would be scorched far beyond anything life could survive. Out at Saturn, nearly 10 times farther from the centre than the Earth is now, the ice you were standing on would flash to vapour. The gentle cold of the outer solar system would become an inferno. There is no comfortable orbit around a star like this, no habitable zone in any sense we would recognise, because the star pours out so much power that it would sterilise its surroundings for enormous distances in every direction. This is not a sun you could live near. It is a sun you could only witness briefly, before it destroyed you. And that tells you something about why we do not find life clustered around the larger stars. The giants are magnificent, but they are hostile, brief and violent, exactly the wrong conditions for the slow patient chemistry that life seems to need. Life, as far as we can tell, wants a small, steady, long-lived star, one that stays quiet for billions of years and does not roast or explode its neighbourhood. It wants a star like our sun. The monsters get the size and the glory and the record books. The modest stars get the worlds where someone might actually be around to look up and notice. Keep that trade in your mind, because it is going to matter more and more as we go. Now, I have been showing you this star at its most overwhelming, filling the sky, swallowing planets, drowning out the sun, and you would be forgiven for picturing it as something impossibly dense and heavy, a solid mountain of fire crushing everything with its bulk. But here is where this star turns from merely enormous into genuinely bizarre, and where our journey takes its first real turn. Because for all its size, for all the planets it could swallow, and all the light it pours out, if you actually tried to touch this star, to fly into it, to find the surface you have been staring at, you would discover something that sounds impossible. There is almost nothing there. This monster, this planet-devouring giant, is one of the emptiest, most tenuous objects in the entire galaxy. And understanding how something can be that large and that insubstantial at the same time is going to change the way you picture stars completely. Part 6. How do you weigh a ghost? Here is the fact that breaks most people's picture of what a star is. Westerlund 1-26, this object large enough to swallow the orbit of Jupiter, contains only a few dozen times the mass of the Sun. Let that sit next to what you just learned about its size. It holds around 1 billion times the Sun's volume, but only a few dozen times the Sun's material. All that size, and almost none of the substance you would expect to fill it. The star is enormous and nearly empty at the same time. Work through what that means for its density, for how tightly packed its material actually is, because the answer is genuinely hard to believe. Our Sun, on average, is denser than water. If you could somehow scoop up a bucket of average Sun and a bucket of water, the Sun would weigh more. That already surprises people, who tend to imagine the Sun as a wispy ball of flame. But now take that same amount of material and spread it out across 1 billion times more space. The density collapses. On average, Westerlund 1-26 is thousands of times less dense than the air you're breathing right now. Not less dense than water, less dense than air by a wide margin. And in its outer layers, the situation is even more extreme. The gas out near the visible edge of the star is thinner than what we would call a decent vacuum in a laboratory on Earth. If you could bottle a jar of it, you would call the jar empty. This is why I keep insisting that the star has no real surface, and I want to make that concrete, because it is one of the strangest things about these giants. When you look at the Sun, you see what appears to be a sharp edge, a clean disk against the black. That edge is not solid. It is simply the depth at which the gas becomes thick enough to be opaque, the layer where the light we see comes from. There is nothing to stand on there, and nothing to run into. For a giant like our monster, that fuzzy boundary is even softer and more gradual. If you flew a ship toward it, you would not smack into anything. You would simply notice the thin gas around you slowly thickening, growing warmer and redder and more crowded, over a distance longer than the entire span of our solar system, without ever passing a moment where you could say, "Here, this is the surface. This is where the star begins." The star does not have an edge. It has a gradient. It fades into existence out of the near vacuum of space, the way fog thickens as you walk into it, except this fog is hundreds of millions of miles thick. So let me return to that phrase I asked you to hold on to, room to spare. When we set this star down in place of the Sun and watched it swallow the planets, room to spare meant excess, a size so large it overflowed the solar system. But now the phrase turns, and it means something different. There is room to spare inside this star in the most literal sense. It is mostly room, mostly space, mostly nothing. If you could journey inward from its faint outer edge toward its centre, you would travel for an enormous distance through gas so thin it is barely there, and only very gradually would it gather into something substantial. This is not a solid monster crushing planets under its weight. It is something far stranger, a titan made mostly of emptiness, a mountain that is somehow also a cloud. The size is absolutely real. The solidity is an illusion, and I find that, honestly, more unsettling than if it were dense, because it means the largest things in the universe are not the heaviest. They are in a way the most hollow, all of which raises a fair question, one you might be asking already. If this star is so far away, so hidden behind dust, so fuzzy at the edges and so prone to changing, then how does anyone measure it at all? How do we put numbers on a ghost 15,000 light-years away that we cannot even see with ordinary light? This is where the human side of the story comes in, because measuring this star has been one of the harder problems in stellar astronomy, and the difficulty is exactly why its size carries a range instead of a single confident figure. Start with the dust. As I mentioned, the curtain between us and the cluster dims the visible light by a factor of around 100,000, roughly 13 steps down the astronomer's brightness scale. In ordinary visible light, the star is all but erased. But dust that blocks visible light is far more forgiving to longer wavelengths, to infrared and radio waves, which slip through the murk where visible light gets scattered and absorbed. So almost everything we know about this star, we learned by looking at it in these longer wavelengths, in the heat glow and the radio hum rather than the light your eye could register. It is a little like getting to know someone you have only ever seen as a silhouette through a frosted window. You can make out the shape, the size, the movement, but you're always working through a veil. Then there is the problem of distance, which quietly poisons everything. To know how large a star truly is, you first have to know how far away it is, because a star's apparent brightness depends on both its true output and its distance. Get the distance wrong, and the size comes out wrong with it. And the distance to this cluster is genuinely uncertain. Different methods place it anywhere from about 12,000 to over 15,000 light-years away, and that spread alone is enough to swing the estimated size of the star. This is not a small technical footnote. It is the single biggest reason the radius comes with a range from around 1100 to 1500 times the Sun, and why that unlikely upper figure exists at all. The star is not fuzzy because astronomers are careless. It is fuzzy because it sits at the edge of what our instruments can pin down. There is one more complication, and it is my favourite, because it means the star is not even holding still to be measured. Giant stars near the end of their lives do not shine steadily. They pulse. They swell and contract over months and years, brightening and dimming as their outer layers heave in and out, unstable in a way smaller stars are not. So when you ask, how big is Westerlund 1-26, part of the honest answer is, big compared to when? The star itself is breathing, slowly, on a scale of time and size that dwarfs anything in our experience, its outer layers rising and falling by amounts larger than the entire orbit of the Earth. Trying to assign it one fixed radius is a little like trying to measure the exact size of a slow, enormous heartbeat. You can capture a range. You cannot capture a single frozen number because the star will not stop moving long enough to give you one. There is one more clue astronomers use to take the measure of this star, and it hangs in the space around it. Surrounding Westerlund 1-26 is a faint shell of glowing gas, a nebula of the star's own making, material it has cast off from its outer layers and pushed out into the space around it. That nebula is not just decoration, it is evidence, a record written in gas of how much the star is losing and how fast. By studying the shape and the glow of that cast-off material, astronomers can work backward toward the star's behaviour, how violently it is shedding itself, how its winds are blowing, how unstable its outer layers have become. The star is, in effect, leaving a trail of its own substance, and we read that trail the way a tracker reads footprints, learning about the animal from the marks it leaves behind. What that trail tells us is that this star is not in a calm or settled state. It is actively coming apart, throwing off material at a tremendous rate, surrounded by the evidence of its own unravelling. A stable star like the Sun does not do this. The Sun loses a mere trickle of material in its gentle wind, nothing like the shell of gas surrounding our monster. That nebula is the mark of a star living at the very edge of what it can hold together, and it is one more reason astronomers know that what we are looking at is not a star in the prime of life, but one in the drawn-out, spectacular process of dying. The evidence is written all around it, glowing faintly in the dark for anyone with the right eyes to read. I find something quietly satisfying in all of this, and I want to name it before we move on. We're standing in front of an object we cannot see with our own eyes, that hides behind dust, that has no solid edge, that pulses and changes, that sits at a distance we can only bracket. And despite all of that, human beings, working from a small wet planet 15,000 light-years away, have measured it. Not perfectly, but well enough to say with confidence that it is one of the largest single objects we have ever found. That is not a failure of certainty. That is one of the quiet triumphs of science, the ability to reach across an impossible distance and weigh a ghost. But knowing how big it is only sharpens the real question, the one we have been circling since we arrived. How does a star get this way in the first place? What could possibly take an ordinary sun and swell it into something 1,000 times wider and mostly made of emptiness? To answer that, we have to go inside. Part 7. Why a star becomes a Titan. To understand how this star became a Titan, we have to go back to what it was born as, because it did not start out looking anything like this. Every star, including our own Sun, spends most of its life in a state of quiet balance. In the core, hydrogen is being fused into helium, and that fusion releases energy that pushes outward as heat and pressure. At the same time, the star's own enormous gravity is pulling everything inward, trying to crush the star down into a point. For most of a star's existence, those two forces hold each other in a near-perfect standoff. The outward push of fusion exactly balances the inward pull of gravity, and the star sits there, stable, steady, burning through its fuel for millions or billions of years. Our Sun has been doing this for 4.5 billion years, and will keep doing it for billions more. That balance is what a normal star's life is. Now, Westerlund 1-26 was never a modest star like the Sun. It was born as one of the giants of that crowded cluster, starting with dozens of times the Sun's mass. And mass, for a star, is destiny. The more massive a star is, the more fiercely gravity squeezes its core, the hotter that core runs, and the faster it burns through its fuel. A star like this does not sip its hydrogen over billions of years. It devours it, blazing with the light of hundreds of thousands of suns, running through its core hydrogen in just a few million years. It lives fast because it has no choice. The same gravity that gives it its power also drives it to burn recklessly, and that reckless pace is the first step on the road to becoming a monster. Here is what happens when the core hydrogen finally runs low, and this is the turning point in the whole story. Fusion in the core sputters, and for the first time in the star's life, the outward push weakens. Gravity, which has been waiting patiently the entire time, begins to win. The core starts to contract, squeezing down on itself, and as it contracts it heats up because compressing a gas always heats it. That rising heat does two things. It ignites a shell of hydrogen fusion in a layer around the shrinking core, and it floods the star's outer layers with more energy than they have ever had to handle. The core is collapsing inward and heating up, while at the same time it is pouring more power outward than ever before. And the outer layers of the star respond to that flood of energy in the only way they can. They expand, enormously. This is the moment an ordinary star becomes a giant. The outer envelope balloons outward, swelling to hundreds and then more than 1,000 times its original size, and as it spreads across all that new space, it cools. A gas that expands always cools, the same way the air escaping a can feels cold on your hand, and so the surface temperature of the star drops from the white-hot glare of its youth down to a cool, sullen red, only around 3,000 degrees. The star has not gained much mass. It has simply redistributed the mass it has across an enormous new volume, inflating like a slow explosion frozen in the act. What was a compact, furious blue star becomes a swollen, cool red one, thousands of times larger and utterly transformed. That is how you build a Westerlund 1-26, not by adding material, but by inflating what is already there into something that overflows a solar system. There is a beautiful piece of physics hiding in why the star has to get quite so large, and it is worth a moment because it explains the size directly. The total amount of light a star gives off depends on two things: how hot its surface is and how much surface it has. A hot star can pour out enormous light from a relatively small surface, because heat is a powerful lever. But our monster's surface is cool, only half the temperature of the Sun. A cool surface is a weak radiator, and yet this star needs to shed the energy of hundreds of thousands of suns, because that fierce shell fusion is generating it whether the star likes it or not. So how does a cool, weak radiating surface get rid of that much energy? The only way it can, by becoming enormous. If each patch of surface can only radiate weakly, then you simply need an almost unimaginable amount of surface, and so the star swells until its total glowing area is large enough to carry away all that power. The size is not an accident or an excess. It is a solution. The star is exactly as large as it must be to survive the energy pouring out of its core, no larger and no smaller. Its monstrous size is the physical answer to an impossible plumbing problem. Let me take you down to that surface now, or rather to the place where a surface should be, because seeing it will tell you something the physics alone cannot. Come with me, and we will descend slowly toward the red glow. You're dropping now through the thin outer gas, and at first there is almost nothing, just a faint reddish haze thickening around you. Then, below, the surface resolves, and it is not smooth. It is a churning, restless expanse of glowing cells, enormous rounded blisters of red-hot gas, each one rising up from far below, spreading across the top, cooling and sinking back down. These are convection cells, the same process you see in a pot of boiling water, hot material rising and cool material falling, except each of these cells is a continent of fire larger than the orbit of a planet. They swell and collapse over months and years, slow enough that in any single moment they seem frozen, huge enough that a single one could contain worlds. There is no ground beneath them. As you sink lower, the gas simply grows warmer and denser and brighter, closing around you, and you understand at last that you're not landing on anything. You're falling into a bottomless red ocean that has no floor, only thicker and thicker layers of glowing gas all the way down toward a core you will never reach. Nothing here is solid, everything is in motion, and the sheer scale of that motion, cells the size of planetary orbits heaving up and down in near silence, is something the human mind can watch but never quite accept. There is a rhythm to that churning surface that is worth pausing on, because it connects to why the star's size keeps shifting. Those enormous convection cells, each one larger than a planet's orbit, do not hold still. They rise, spill their heat, and sink over months and years, and as they do, the whole outer body of the star heaves gently in and out, brightening and dimming in a slow, irregular pulse. On a smaller, denser star like the Sun, the convection cells are tiny by comparison, and the surface stays relatively calm and well-behaved. But on a giant this swollen and this loosely bound, the convection is enormous and unruly, and the surface is never quite the same size from one year to the next. When astronomers say the radius is uncertain, part of what they are admitting is that the star itself does not have one fixed radius. It is always breathing, its glowing skin forever rising and falling by amounts larger than the distance from the Earth to the Sun. Underneath all of this is a single, unrelenting struggle, and it helps to name it plainly. Every star is a contest between two forces that never rest, gravity pulling everything inward and the energy of fusion pushing everything outward. For most of a star's life, those forces are evenly matched, and the star is calm. But a red giant like this one is a star where the match has become desperate and lopsided, where the outward flood of energy has bloated the star far past its comfortable size, and the grip of gravity on those distant outer layers has grown weak and tenuous. The star is holding itself together by the thinnest of margins, its outer skin barely bound, its surface trembling, its material leaking away into space. It is not a stable object calmly shining. It is a slow motion crisis, a struggle so finely balanced that it can only last a little while longer before one side finally wins, and we already know which side wins in the end. Pull back out now, into the calm of space, and hold what you just saw, because it reframes everything. This star is not a solid object at all. It is a process, a slow and violent balancing act between a collapsing core and an inflating envelope, held together by nothing but its own gravity, churning constantly, breathing in and out, shedding its own material into space. It is less like a rock and more like a storm, an enormous, patient, planet-swallowing storm that has been raging for millions of years. But no storm lasts forever, and here is the part of the physics that turns our wonder towards something heavier. Everything I have just described, the swelling, the cooling, the furious burning, is not a stable condition. It is a symptom. It is what a star looks like in the act of dying. And Vesterlund 1-26 is sitting very close to an invisible line, a limit written into the laws of physics themselves, beyond which no star of this kind is allowed to exist. To understand how close to the edge this monster really is, we need to talk about that limit, and about the strange, exclusive family of giants that live right up against it. Part 8. The Edge of What's Possible. There is a ceiling on how large and luminous a star can be, and it is not a suggestion. It is written into the physics. Astronomers call it the Humphreys-Davidson limit, named for the two researchers who first noticed that when you plot the brightest stars by their temperature and their output, the top of the chart is simply empty. There are no cool red stars above a certain enormous luminosity. None. You find hot blue giants up there, but the cool red ones stop at a hard edge, as if someone had drawn a line and forbidden anything to cross it. And something has. What forbids it is the star's own power. Above that limit, a star pouring out that much energy cannot hold its swollen outer layers together at all. The radiation pushing outward becomes so intense that it overwhelms gravity's grip on the surface, and the star begins tearing its own outer layers off and flinging them into space. Instead of settling into a stable red giant, it strips itself back down, blowing away its envelope and turning into a hot, naked, furious star of a different kind. The cool red giants simply cannot exist beyond that boundary, because any star that tries gets shredded before it can. Westerlund 1-26 lives right up against that line. It is close to as large and as luminous as a cool red star is physically permitted to be before the universe stops allowing it. That is a big part of why it is so rare, and why we had to travel 15,000 light-years to find one. These are not common objects scattered on every corner. They are a tiny handful of stars sitting at the extreme edge of what stellar physics will tolerate, each one balanced on the knife's edge between holding together and blowing apart. And the circumstellar nebula we mentioned earlier, that faint shell of gas surrounding the star, is the visible proof that it is already losing the fight, already shedding its outer material into space, already beginning to come apart at the seams. It is not comfortably enormous. It is dangerously enormous, as large as it can get and no larger, which is a very precarious place for anything to be. This raises a question people always ask, and I want to answer it honestly rather than for drama. Is Westerlund 1-26 the largest star in the universe? And the truthful answer is, we do not know, and it is probably not. And the reason why is more interesting than a simple yes would be. There is a small, exclusive family of stars that all sit near this same extreme edge, all competing for the title, and the ranking among them keeps shifting as our measurements improve. There is a star called Stephenson 2-18, buried in another distant cluster, which some estimates place at over 2,000 times the Sun's radius, larger even than our monster, though that figure is shaky enough that many astronomers doubt it, because it seems to push past the theoretical limits we just discussed. There is a star called WOHG 64, sitting all the way out in a neighbouring galaxy, estimated at around 1,500 times the Sun. There is RW Cephei, and there is the famous Viosicanis Majoris, each of them a red giant of staggering size, each with its own uncertain measurement. The most instructive case of all is a star called UY Scuti. For years, UY Scuti was crowned the largest known star, quoted everywhere at around 1,700 times the Sun's radius, the reigning champion of size, and then astronomers got a better measurement of its distance. Because a more accurate distance changes everything downstream, the new figure did not just tweak the number, it cut UY Scuti down to less than half its supposed size, dropping it from the top of the list to a far more modest rank, all without the star itself changing in the slightest. Nothing happened to UY Scuti, only our knowledge changed, and that is the honest lesson hiding inside this whole question. The title of largest star is not really a fact about the universe, it is a snapshot of the current state of our measurements, and those measurements, out here at the ragged edge of what we can detect, are always shifting. Westerlund 1-26 is unquestionably one of the largest stars we have ever found. Whether it is number 1 or number 4 or number 7 on any given year depends on distances we are still refining. I find that more honest and more interesting than a false certainty. The truth is that we are looking at a small club of the largest objects the universe seems able to build, and our monster is a full member of that club, jostling near the very top. Whatever its exact rank, its reach is almost impossible to overstate, and I want to show you that reach with one last demonstration before we turn toward its fate. We have stood inside the star's body and swallowed the planets. Now let us back all the way off and ask how far away you would have to go before this thing stopped dominating your sky. Imagine a planet orbiting Westerlund 1-26 at a distance of 400 astronomical units. That is 400 times the distance from the Earth to the Sun, an orbit so enormous that a single trip around it would take that planet many thousands of years. From that distance, our own Sun would be reduced to a bright star, just one more point of light, easily lost among its neighbours. Surely from 400 times the Earth's distance, even this monster would shrink to a manageable dot. Come stand on that faraway world and look up. The star has not shrunk to a dot. It still hangs in the sky as a distinct brooding red disk, large enough to see as a shape rather than a point, painting the whole horizon in its dull crimson light, refusing to be diminished by a distance that would erase our sun completely. There is no real night here. The star is always there, always looming, a red presence 400 times farther away than the Earth is from the sun, and still the most dominant thing in the heavens. Let me give you one more marker to feel that distance. The Voyager 1 spacecraft, the farthest human-made object ever launched, has been flying outward from Earth for almost 50 years, and it has travelled only about 170 astronomical units. Our hypothetical planet sits more than twice as far out as Voyager has managed to travel in half a century, and from that enormous remove, this star still owns the sky. That is the reach of the thing we came to see. It is worth sitting for a moment with just how strange that ceiling is, the Humphreys-Davidson limit, because it is one of those places where nature seems to enforce a rule without any referee. Nobody decided that cool red stars should stop at a certain size. There is no law written in a book. And yet when astronomers plotted thousands of the brightest stars, the pattern was unmistakable. The upper region of the chart, where the cool giants larger and brighter than our monster would sit, is simply blank. Nature does not build them. Or rather, when nature tries, the star immediately begins destroying itself, blowing away its own outer layers so furiously that it cannot stay in that cool, swollen state, and it retreats to something hotter and smaller. The emptiness at the top of that chart is not missing data. It is a forbidden zone, patrolled by the star's own physics, and Westerlin 1-26 is parked right up against its fence. That fence is also why the exact ranking of the giants is so slippery, and why I keep refusing to simply crown a single largest star and be done with it. Every one of these record holders sits at the extreme edge of what we can measure, half hidden by dust, wrapped in its own shed material, pulsing and changing, at a distance we can only estimate. Each new measurement of distance, each better instrument shuffles the deck again. A star that was the largest known one year gets a revised distance the next year and tumbles down the list, the way UY Scooty did, without anything about the star itself changing at all. So when you see a confident claim that one particular star is definitively the largest in the universe, treat it gently. What is really being said is, this is our current best guess, from our current best data, and it will very likely change. That honesty is not a weakness of the science. It is the science working exactly as it should, out at the edge of the possible where certainty is the one thing nobody can afford. I have spent all this time showing you how large this star is, how luminous, how rare, how close to the very limit of what is possible. And there is a temptation, standing in front of something this enormous, to feel that you are looking at the most powerful, the most permanent, the most invincible kind of object the universe can make. Surely something this large is here to stay. Surely something that swallows solar systems and outshines hundreds of thousands of suns has nothing to fear. But that instinct is exactly backwards, and correcting it is where this journey stops being about size and starts being about something closer to the bone. Because everything you have learned to admire about this star, its enormous size, its ferocious output, its place at the edge of possibility, is not a sign of strength at all. Every one of those things is a symptom of how quickly it is dying, and our own small, unremarkable sun is going to outlive this monster by a margin so wide it will change how you feel about the word big. Part 9. The Price of Being Enormous. We tend to assume that bigger means longer lasting. In our everyday world it usually does. A large candle burns longer than a small one. A large animal often lives longer than a small one. A mountain outlasts a sandcastle. So it feels natural to look at the largest star we have ever seen and assume it must also be one of the most enduring, a fixture that will hang in its cluster for ages. With stars, though, the rule runs exactly the other way, and once you understand why, you cannot unsee it. Among stars, the biggest are the most short-lived, by an enormous margin, and Westerlin 1-26 is a spectacular example of the price that size demands. Think back to how this star got so large in the first place. It began with dozens of times the Sun's mass, and that heavy mass squeezed its core so hard that it burned its fuel at a furious, reckless rate, shining with the light of hundreds of thousands of suns. That brilliance we admired, that fire hose of light pouring out across the galaxy, is not free. It is fuel being consumed, and consumed fast. A star can only shine so brightly for so long before the tank runs dry. Our Sun, modest and dim by comparison, sips its hydrogen so gently that it can keep burning steadily for roughly 10 billion years. Westerlun 1-26, blazing hundreds of thousands of times brighter, tears through its entire fuel supply in only a few million years. It is the difference between a candle left to burn quietly through a long night and a fistful of flash powder thrown into a fire. One lasts, the other flares magnificently and is gone. Sit with the arithmetic of that, because it is genuinely startling. Our Sun will live for something like 10 billion years. This monster will live for only a few million. That means our small, ordinary, easily overlooked Sun will shine for roughly 1,000 times longer than the largest star we have ever found. 1,000 times longer. Everything about Westerlun 1-26 that made your jaw drop, its size, its output, its reach across the galaxy, comes at the cost of almost everything we would call longevity. It bought its enormity by agreeing to die young, and it is not even a fair trade in the star's favour. It gets a few million years of glory. The Sun gets 10 billion years of steady, life-sustaining warmth. If you were a star and you could choose, it is not obvious the monster made the better bargain, and Westerlun 1-26 is not at the beginning of its short life. It is near the end. The swollen red giant phase we have been marvelling at is not a stage a star spends most of its life in. It is the final chapter, the last brief act before the end, lasting only a tiny fraction of the star's already brief existence. When we see a star this large and this red, we are not looking at a young, thriving object. We are looking at one in its death throes, its core already changing, its outer layers already unstable and blowing away. That nebula of gas surrounding it, that faint shell we can detect, is the star's own substance being cast off into space, layer by layer, as it comes apart. It is quite literally shedding itself. Every year it grows a little more tenuous, a little more unstable, a little closer to the end. We arrive to find a Titan, and the Titan is dying in front of us, in slow motion, on a timescale so long that within a human lifetime it looks perfectly still, and yet it is unmistakably, irreversibly on its way out. Here is where I have to be careful and honest with you about time, because the distances we have been discussing do something strange to the very idea of when. Remember that this star is 15,000 light-years away, which means everything we see of it left the star 15,000 years ago. We are not watching the star as it is. We are watching the star as it was back when the last ice age still held the Earth. So when I tell you this star is near the end of its life, I have to add a genuinely unsettling possibility. Given how close to the edge it already was 15,000 years ago, it is entirely possible that Westerlun 1-26 has already died. It may have already exploded, already torn itself apart in the enormous detonation that ends stars like this, and we simply would not know, because the light carrying that news has not yet crossed the 15,000 light-years between us. The star you are looking at right now, this instant, may not exist anymore. Its final flash could already be racing toward us across the galaxy, still thousands of years from arrival. We would keep seeing the calm red giant, night after night, for millennia, long after the star itself was gone. Out here, even the question of whether something still exists does not have a clean answer. Let me slow down and say plainly the thing this whole part has been building toward, because I think it is the quiet centre of everything we came here to find. We travelled 15,000 light-years to stand in front of the largest, most powerful, most overwhelming star we have ever discovered, a thing that swallows solar systems and outshines hundreds of thousands of suns. And what we actually found, when we looked closely, was something fragile, something temporary, something already dying, already shedding itself into the dark, possibly already gone. All that size is not a monument to permanence, it is a countdown, running fast. The star is enormous precisely because it is burning itself out, and the very qualities that make it magnificent are the same qualities that doom it. Bigness out here is not strength, it is not safety, it is a brief, brilliant, spectacular way of dying young. Let me make that lifespan difference land in a way you can feel in your body, because the raw numbers slide by too easily. Imagine compressing the entire 10 billion year life of our Sun down into a single year, from January to December. On that scale, the Sun burns steadily for all 12 months, a whole year of quiet warmth. Now place Westerlund 1-26 on that same calendar. A star that lives only a few million years against the Sun's 10 billion would burn for something like a few hours. Not months, not weeks. A few hours out of an entire year, and then it would be gone, exploded, finished, while the sun kept right on shining through all the months that followed. The monster is a firework that goes off in the small hours of a single morning. The sun is the steady daylight that lasts the whole year long, and we, and everything we care about, are children of the daylight, not the firework. This is the part that quietly rearranges how you feel about the whole trip. We came all this way to be impressed by the largest, most powerful star we could find, and we should be impressed, because it is genuinely one of the most enormous objects in existence. But power and size, in a star, turn out to be the very things that guarantee an early death. The giant is not winning at being a star. In a sense, it is losing faster and more spectacularly than anything else in the sky. It traded everything, its whole future, for a few hours of unimaginable brilliance. And meanwhile, the modest, overlooked, unglamorous stars, the ones nobody makes films about, the ones like our own sun, are quietly outlasting the giants 1,000 times over, keeping their worlds warm through the long, slow ages that life actually needs. It makes you wonder whether we have been measuring the wrong thing all along. And then there is our sun, back home, the star we watched shrink to an anonymous speck at the very beginning of this journey. Small, ordinary, utterly unremarkable next to this red giant. Easy to overlook, one dim yellow dot among 400 billion, and yet that modest little star will still be shining, steady and warm, long after this monster and every giant like it in that crowded cluster has exploded and faded to a cold remnant. It will still be shining long enough to have kept a small blue world warm and wet and alive for billions of years, long enough for creatures on that world to evolve, look up, build instruments, and reach 15,000 light-years across the galaxy to measure a dying titan they will never visit. Suddenly the word big has two very different meanings, and I am no longer sure the monster owns the more important one. But size, however we weigh it, is only half of this star's story. The other half is the neighbourhood that made it, because the cluster we pass through on the way in is not just a backdrop. It is a factory, and the things it builds are even stranger than the monster at its centre. Part 10. A city that makes monsters and magnets. When we first arrived, I described Westerlund 1 as the most crowded stellar city in the galaxy, and I called it a factory for violent objects. Now that you have seen what it produced at its centre, I want to take you back into that crowd, because the monster is not the only remarkable thing living here. This cluster has built something else, something smaller than our red giant by an almost comic margin, and yet in its own way even more extreme. To find it, we have to wait for one of these giants to finish dying, and see what it leaves behind. When a massive star reaches the end, it does not simply fade out. It collapses and detonates as a supernova, and in the ruin at the centre of that explosion, the crushed core of the star can be left behind as one of the strangest objects in physics, a neutron star. Take something more massive than the Sun and crush it down until it is only a dozen or so miles across, a city-sized ball so dense that a single sugar cube of its material would weigh as much as a mountain, and you have a neutron star. Westerlund 1, with all its dying giants, has made at least one. But the one it made is not an ordinary neutron star. It is a magnetar, and a magnetar is what you get when that crushed core is also wrapped in the most powerful magnetic field known to exist anywhere in the universe. It is genuinely hard to convey how strong a magnetar's magnetic field is, because the number is so far outside anything we handle. The magnetic field of a magnetar can be something like 1,000 trillion times stronger than the Earth's magnetic field, the gentle field that nudges your compass needle north. Physicists like to illustrate it this way. If a magnetar sat where the moon sits, 250,000 miles away, its magnetic field would be strong enough to wipe the data off every credit card on Earth and pull the keys out of your pocket. Get anywhere close to one, within 1,000 miles, and the field would not just affect your equipment. It would distort the very atoms in your body, stretching them into thin needles and unravelling the chemistry that keeps you alive, killing you in a way no human has ever died, torn apart at the level of your molecules by nothing you could see or touch. This object, this magnetar in Westerlund 1, was discovered by the Chandra X-ray Observatory in the year 2005, and it is one of only about 24 such objects known in the entire galaxy. And it lives right here, in the same cluster as our red monster, two of the most extreme objects in the universe sharing a single small neighborhood. Here is where the magnetar hands us a real mystery, one that astronomers are still working to explain, and it tells us something surprising about how these giants die. When astronomers studied this magnetar, they worked out roughly how massive its parent star must have been, the star that exploded and left it behind. The answer came out to more than 40 times the mass of the Sun, and that is a problem, because a star that heavy is not supposed to leave a neutron star at all. A star that begins with more than 40 times the Sun's mass is expected to collapse all the way into a black hole when it dies, its core so heavy that nothing can stop the fall. Instead, this one left a neutron star, a magnetar, an object that only forms from a lighter core. So where did all the extra mass go? The leading explanation is remarkable. Before it died, the parent star must have shed more than 95% of its original material, throwing away almost its entire enormous bulk, so that by the time it finally collapsed, only a neutron star's worth of core remained. More than 95% gone before the end. How does a star throw away almost all of itself? The most likely answer is that it did not do it alone. It probably had a companion, a second star orbiting close beside it, and that companion helped strip away its outer layers, pulling and tearing the giant's material off over time until almost nothing was left but the core. And there is a haunting piece of evidence for this. Astronomers have spotted a star being flung out of the cluster at high speed, a runaway, racing away from Westerlund 1 as if it had been kicked. The best explanation is that this runaway was the magnetar's longtime companion, the very star that helped strip the giant down, sent flying when its partner finally exploded, and the pair was torn apart by the blast. Two stars bound together, one slowly cannibalizing the other, until the moment of death threw the survivor across the galaxy. That is the kind of drama this quiet-looking cluster has been staging behind its curtain of dust. Step back and take in what this one crowded knot of stars contains. At its center, a red giant so large it would swallow the solar system. Elsewhere in the same crowd, a magnetar, the strongest magnet in the known universe, left behind by a star that somehow threw away almost all of itself. Around them, a couple dozen Wolf-Rayet stars blazing with savage light as they boil away their outer layers, half a dozen rare yellow hypergiants heaving unstably, a temperamental luminous blue variable, and dozens of other massive stars all racing toward their own violent ends. And every 10,000 years or so, on average, one of them explodes. This is not a peaceful town. It is an assembly line for the most extreme objects physics permits, running continuously, turning out monsters and magnets and remnants, one dying giant at a time. Every one of these objects came from the same single burst of starbirth a few million years ago. They are all siblings, and they are all, in their different ways, doomed. Let me linger on the neutron star at the center of all this, because it may be the single most extreme kind of object we have ever confirmed exists, and it came out of this very cluster. When the core of a dying giant collapses, the crush is almost beyond comprehension. Protons and electrons, the ordinary building blocks of atoms, are squeezed so hard that they are forced together into neutrons, and the entire core, once larger than the Earth, is packed down into a ball only about a dozen miles across. The density that results is staggering. A single teaspoon of a neutron star material would weigh about as much as a mountain, crushed into the volume of a sugar cube. The surface gravity is so intense that if you could somehow stand on it, you would be flattened instantly into a film thinner than a sheet of paper. This is not exotic theory. These objects are real. We detect them across the galaxy, and this cluster made one. Now wrap that already impossible object in the strongest magnetic field known to physics, and you have the magnetar. What makes the magnetar in Westerlund 1 such a puzzle, and such a gift to astronomers, is the accounting problem it created. Its parent star was heavy enough that it should have skipped the neutron star stage entirely and collapsed straight into a black hole. The fact that it did not, that it left this spinning, magnetized city-sized remnant instead, is a loud signal that the star found some way to throw off almost all of its enormous mass before the end. And the leading suspect, that runaway star we saw fleeing the cluster, turns the whole thing into a story with two characters. Picture them, two massive stars locked in a tight orbit, one of them slowly stripping the other, pulling its outer layers away across ages, until the stripped star finally collapses and detonates, and the violence of that death flings its lifelong partner across the galaxy at tremendous speed. The magnetar is what was left of the victim. The runaway is the thief, still fleeing the scene millions of years later. That is the kind of history hidden in this crowd, and our monster is headed for a chapter of its own. And that returns us finally to our own monster, because Vestalun 1-26 is going to take its place in this grim assembly line. It is one of the dying giants. Its turn is coming. When it goes, it will not simply wink out. It will do what its siblings have done, what the magnetar's parent did, what this cluster has done 1,000 times over. It will detonate. And because this star is so enormous, so luminous, so close to the very limit of what a star can be, its death is going to be one of the most violent single events the universe knows how to produce. We have seen how it lives. We have seen the family it belongs to. Now it is time to see how it dies, and to watch the beacon that would not go out finally, spectacularly, go out for good. Part 11. The Last Light. The death of a star like this begins, strangely, far down in its core, in a place we can never see, with a quiet crisis of fuel. All through its life, the star has survived by fusing lighter elements into heavier ones, releasing energy with each step, first hydrogen into helium, then, as the core heats further near the end, helium into carbon, carbon into heavier elements still, each stage burning faster than the last. In its final phase, the star becomes layered like an onion, shell within shell, each one fusing a heavier element, the whole structure racing through in a frantic rush. The outermost shells might burn for thousands of years, but the innermost ones burn through in a matter of days, then hours, and then the core reaches iron. Iron is the wall. When you try to fuse iron, it does not release energy, it absorbs it. The furnace that has held the star up against its own gravity for millions of years suddenly, catastrophically, stops paying out. And with nothing left to push back, gravity, patient gravity, finally gets everything it has been waiting for. What happens next is almost too fast to describe. The core, an object larger than the Earth, collapses in on itself in less than a single second, falling inward at 1/4 of the speed of light, crushing down until it can crush no further, until its material is packed as tightly as the inside of an atomic nucleus, and then it rebounds. The infalling matter slams into that ultra-dense core and bounces, and a shockwave of unimaginable power tears back outward, ripping up through all those layers, blasting the entire outer body of the star into space. In that instant, more energy is released than the star has given off in its entire multi-million-year life. Let me put you there, at a safe and impossible distance to witness it, because there is nothing else like it in nature. You're watching the red giant hang there, calm and enormous, the way it has looked for all the time we have known it. Then, without warning, its centre brightens. A point of light appears far within the red, and in seconds it swells and intensifies, racing outward through the star's own body, faster and brighter, until the entire enormous sphere, that thing larger than the orbit of Jupiter, erupts. A wall of light and matter explodes outward in every direction, tearing through layers larger than our whole solar system, and for a few weeks this single dying star blazes brighter than every other star in its galaxy combined, brighter than hundreds of billions of suns, a single point outshining an entire pinwheel of stars. The light of it would be visible clear across the universe, and in the heat of that blast, in those final furious moments, the explosion forges the heaviest elements there are, and flings them out into space, seeding the darkness with the raw material of future worlds. Then, slowly, over months and years, the brilliance fades, and where the largest star we ever found once hung, there is only an expanding cloud of glowing debris, drifting outward into the cluster, and at its centre a small, dense remnant, all that is left of a Titan. I asked you at the very start to hold on to an image, the red beacon that would not go out, the star still visible as a stubborn spark even after we had left the entire galaxy behind. Here is where that image comes back, transformed. For all of its long life, this star has been a beacon that refused to fade, pouring out the light of hundreds of thousands of suns, holding its place in the sky through everything, and its final act, its death, is the brightest that beacon will ever burn, a farewell flash outshining a galaxy, the most luminous moment in the star's entire existence saved for the very end. And then, after that impossible flash, For the first time in millions of years, the beacon goes out. The light that could be seen from outside the galaxy is extinguished, replaced by a fading cloud and a silent remnant. The star that would not go out finally does. And what of all that room to spare, the enormous space the star's body occupied, large enough to swallow the inner solar system, in the collapse, it vanishes. The core that fell inward in less than a second erased in that instant a volume larger than the orbit of Jupiter. All that room, all that emptiness the star had spread itself across, gone in a heartbeat, crushed down into a ball a few miles wide or swallowed entirely beyond a point of no return. The room to spare that once meant such abundance becomes, in the end, the measure of how far the star had to fall. Everything it had built itself into over millions of years, it loses in a single second. There is a detail about that collapse that almost nobody expects, and it is one of the most astonishing facts in all of physics. When the core falls and rebounds, the great majority of the energy released does not come out as light at all. It comes out as neutrinos, ghostly particles so reluctant to interact with matter that trillions of them are passing harmlessly through your body every second, right now, from our own sun. In the collapsing center of a dying star, so many neutrinos are produced so violently that even those barely interacting particles slam outward with enough force to help blow the entire star apart. For a few seconds, a dying star can shine more brightly in neutrinos than all the ordinary stars in the observable universe combined. We cannot see that flash with our eyes, but our instruments can catch a whisper of it, and when a nearby star dies, the neutrinos actually reach us slightly before the light does, a silent early warning racing ahead of the visible blast. Then comes the part we can see. The shockwave, having torn its way up from the core through layers larger than our whole solar system, finally reaches the surface and breaks out, and the star erupts into a brilliance that climbs for days and then holds for weeks. At its peak, this single exploding star can outshine the entire galaxy it lives in, hundreds of billions of stars outdone by one dying giant. If Westerlund 1-26 explodes and the light reaches Earth, even across 15,000 light-years and through all that dust, it could become bright enough to see with the naked eye, possibly bright enough to cast a faint shadow at night, a new red point burning in the southern sky where nothing visible had been before. It would hang there for weeks, slowly fading, while people across the world looked up and wondered, most of them unaware that they were watching the death of the largest star humanity had ever measured, an event that had actually happened back when their ancestors were first learning to farm. I have to be honest with you about one thing, because it is a genuine open question, and I would rather share the mystery than fake an answer. We do not know for certain what Westerlund 1-26 will leave behind. A star this massive would ordinarily be expected to collapse into a black hole, a point of gravity so extreme that not even light escapes it. But remember what we learned from the magnetar next door, whose parent star threw away more than 95% of its mass before it died and left a neutron star instead of a black hole. Our monster is already shedding itself, already surrounded by a nebula of its own cast-off material, already losing mass at a tremendous rate. So which will it be? If it holds on to enough of its bulk, it will make a black hole, and a piece of this cluster's space will simply close over and go dark forever. If it sheds enough first, like its sibling did, it might leave a neutron star, perhaps even another magnetar, another impossibly strong magnet spinning in the dark where a giant used to be. We honestly do not know. The largest star we have ever found is going to end as either the deepest kind of darkness the universe can make, or the strongest magnet it can make, and which one is still hidden from us, waiting 15,000 years away. There is one more turn of the knife in all of this, and it is the strangest consequence of the distances we have been living with. Everything I have just described, the collapse, the explosion, the flash brighter than a galaxy, may not be in the future at all. It may already have happened. The star we have been standing in front of, calm and red and enormous, is a 15,000-year-old image, and in the time since that light left, this whole death may already have played out. Somewhere in the space between us and Westerlund 1, the flash of its ending may already be travelling toward Earth, crossing the dark at the speed of light, still thousands of years from arriving. One night, far in the future, long after everyone alive today is gone, the descendants of humanity might look up and see a new point of light appear in the southern sky, brightening over days into something visible even in daylight, the death announcement of a star that actually died in our own distant past. They will be watching the end of a monster that, from its own point of view, perished before they were ever born. And that collision between the enormous and the intimate, between a dying titan and the small fragile creatures who might one day witness its light, is exactly where I want to bring this journey home. Part 12. What the Monster Leaves Us. We have come a long way together, so let me bring us back to where we started, because the journey ends where it began, with our own small sun. At the very start, we watched it shrink behind us from a blinding disk to an anonymous speck, one dim point among millions, and I asked you to hold on to that feeling of smallness. Now that we have stood in front of a star 1,000 times wider, watched it swallow solar systems and outshine galaxies, and die in a flash brighter than everything around it, that smallness might feel even sharper. Next to Westerlund 1-26, the Sun is nothing. Next to the Sun, the Earth is nothing. Next to the Earth, you're so small that no comparison even makes sense. It would be easy to end this journey feeling diminished, like a speck that briefly learned about a giant. But I think that reading gets it exactly backwards, and I want to spend our last few minutes explaining why. Start with something the monster's death gives us, quite literally. When a star like Westerlund 1-26 explodes, it forges the heavy elements and scatters them across space, seeding the darkness with the raw material of everything that comes next. The calcium in your bones, the iron in your blood, the oxygen you're breathing at this very moment, none of it could have formed in a quiet star like the Sun. It was all made inside massive, short-lived giants, and blown out into the universe by their deaths. Every heavy atom in your body was cooked in the core of a dying star and flung into space by an explosion much like the one waiting for our monster. Which means the giants and their violent ends are not distant curiosities that have nothing to do with us. They are our ancestors. We are made of the debris of dead titans. That crowded, violent cluster 15,000 light-years away is doing the same work that, billions of years ago, made you possible. The monster is not separate from us. We are, in the most physical sense, its distant children. Now let me come back to that phrase I've been carrying since the beginning, the one I promised would mean more by the end. Every dot is a sun. When we set out, I said it to fill you with wonder at abundance, to make you feel the sheer number of stars streaming past, 400 billion suns in our galaxy alone, each one a furnace, many with worlds of their own. That was true, and it was worth feeling. But now you know something you did not know then. You know that among all those countless dots, the true giants, the ones like our monster, are fantastically rare. A tiny handful balanced at the very edge of what is possible, and every one of them is burning out fast, doomed by its own size, here and gone in a cosmic instant. And you know that the small, steady, ordinary stars, the ones easy to overlook, are the ones that last, the ones that can keep a world warm long enough for something to grow up on it and start asking questions. Every dot is a sun. But only a small, quiet, unremarkable kind of dot could have been ours. Only the modest ones give you the time. This is the turn I've been walking you toward, so let me say it as plainly and gently as I can. Our smallness is not the tragedy of this story. It is the point of it. Westerlund 1-26 is larger than we can picture, more powerful than we can grasp, and it will never know a single thing about itself. It cannot look outward. It cannot wonder. It burns enormously and briefly and blindly, and then it dies, and in all its staggering size there is no one home to notice. And here, on a grain of dust orbiting an ordinary star, are we, small enough to fit in a room, brief enough that our whole civilization has risen in less time than it takes this star's light to reach us. And yet we are the part of the universe that woke up. We are the part that can build an instrument, pierce a curtain of dust 15,000 light-years thick, measure a dying giant we will never touch, and feel something when we do. The monster has the size. We have the eyes. And of those two, I am no longer sure which is the greater thing. Think about what we actually did together tonight. From a small blue world, without leaving our chairs, we crossed 15,000 light-years, stood inside a star large enough to swallow Jupiter's orbit, floated at a surface with no floor, watched a magnetar form and a giant die, and held in our minds an object so enormous that light needs 6 hours just to circle it. None of that is nothing. That is very close to the most remarkable thing a small creature can do. The universe spent almost 14 billion years building giants that could not appreciate themselves, and then, on at least one quiet world, it built something small enough and strange enough to appreciate them for it. Being small is the price of admission for being the kind of thing that can look up and understand. The monster paid a different price, and got size and glory and an early grave, and never once knew it was alive. There is a symmetry in this that I find almost unbearably beautiful, and I want to leave it with you before we go. The heavy atoms that make you are forged inside dying giants, and scattered by explosions like the one waiting for our monster. That means the story we have been telling is not really about a distant star at all. It is about where you came from. Billions of years ago, somewhere in this galaxy, giants lived and died and seeded the darkness with carbon and oxygen and iron, and that enriched dust eventually gathered into a new cloud, and that cloud collapsed into our sun and its planets, and some of those atoms ended up in the oceans, and then in living things, and then, eventually, in you. You're not separate from the giants. You're what they became. When you look up at Vestalun 1-26, a dying star seeding its own cluster, with the raw material of future worlds, you are looking at the same process that, long ago, made the looking possible. So the universe builds these enormous, blind, short-lived monsters, and out of their ashes, across billions of years, it slowly assembles something small and fragile and awake enough to look back and understand them. The giant cannot know it exists. It cannot feel its own size or mourn its own death or wonder at the cluster it lives in. All of that noticing, all of that wonder, had to wait for something small to come along and do it. That is not a consolation prize for being tiny. It might be the most important thing that happens anywhere in the whole enormous machine, the moment when a corner of the universe finally wakes up enough to see the rest of itself. And it happened here, on this small, warm world, in you. So the next time you're outside on a clear night, and you look up at those faint scattered points of light, I hope you carry a little of this with you. Somewhere out there, hidden behind dust in a crowded stellar city, a red giant larger than our whole inner solar system is quietly finishing its short, brilliant life, maybe already gone, its farewell light still crossing the dark toward a sky it will reach long after we're gone. And here you are, small and warm and brief, kept alive by a modest yellow star that will outlast that giant 1,000 times over, made of atoms forged in explosions like the one still to come, able to know all of this and to feel it. Every dot up there is a sun. Every one is a story. And the fact that you are small enough and alive enough and awake enough to look up and wonder about them at all may be the most extraordinary thing in the entire enormous, indifferent, beautiful universe. That is what the monster leaves us. Not fear and not smallness, but the quiet, astonishing gift of being the ones who get to notice.